Good day, everyone. So we're reviewing Wetzel's Limnology textbook. This is edition number 4. We're on chapter 15, the phosphorus cycle. And right now we're looking at oxygen content of the macrozone, and we're specifically dealing with the macrozone in the sediment. So let's get started. The most conspicuous regulatory features of the sediment boundary are the mud, water interface, and the oxygen content. The oxygen content at this macrozone is influenced primarily by the metabolism of bacteria, algae, fungi, planktonic invertebrates that migrate to and live within the interface, and sessile benthic invertebrates. Microbial degradation of dead particulate organic matter that settles into the apolimnion and onto the sediments is the primary consumptive process of oxygen, which is depleted within a few centimeters of the surface in oligotrophic lakes, but autotrophic nitrification also plays a role. The rate of heterotrophic oxygen depletion at the sediment water boundary is governed by the rate of organic loading to the sediments and the rate of oxygen supply from turbulent mixing from above. For example, it has been estimated that 88% of the apolimnetic oxygen consumption in the central basin of Lake Erie resulted from bacterial degradation of algae sedimenting from the trophogenic zone. These authors estimated that by 2008-2010, heterotrophic respiration consumed 70% of the depleted oxygen and autotrophic nitrification 30%. Nitrification rates depend on supplies of ammonium and other metabolically essential nutrients, including phosphorus and oxygen. Decomposition of more labile organic fractions, largely of plant origins, occurs while it is settling into the sediments, and depending on water column depth and rates of inputs and sedimentation, sediments in deeper water can receive organic residues that are relatively resistant to rapid decomposition. Beneath the sediment surface, oxygen concentration rapidly disappears with sediment depth because oxygen diffusion rates are too low to meet the biological and chemical demands. Sediment demands for oxygen is high and is governed by the intensity of microbial and respiratory metabolism and by the fact that in the anaerobic zone, oxidizable inorganic elements such as ferric iron accumulate from the decomposition of organic matter. Diffusion regulates transport within the sediments unless the superficial sediments are distributed by overlying turbulence, which increases the supply rate of oxygen. Oxygen from well-aerated overlying water, as in oligotrophic lakes or in more productive lakes at periods of complete circulation, will penetrate only a few centimeters into the sediments by diffusion. However, the limited diffusion of oxygen beyond superficial sediments can be overcome to some extent by centimeters-long microbial cables that connect redox couples in the aerobic and anaerobic zones. I'm not sure what they are referring to when they're talking about microbial cables, maybe a string of microbes. The superb early experimental and observational work of Mortimer demonstrated the importance of an oxidized macrozone to chemical exchanges, especially of phosphorus from the sediments. At the sediment surface, a difference of a few millimeters in oxygen penetration is the critical factor regulating the exchange between sediment and water. These relationships are exemplified by two lakes, as described below. With organic sediments, the first lake maintained oxygen concentration at the sediment interface greater than 8 milligrams of oxygen concentration. These relationships are exemplified by two lakes as described below. With organic sediments, the first lake maintained oxygen concentration at the sediment interface greater than 8 milligrams per liter throughout summer stratification, while in the second, lake oxygen levels at the interface decreased to less than 1 milligrams per liter. In the first situation illustrated by Mortimer, studies of Windermere, England, oxygen concentration at the sediment surface did not fall below 1 or 2 milligrams per liter. Electrode potential, which approximate composite redox potentials of the oxygenated overlying water and superficial sediments to a depth of approximately 5 millimeters were uniformly high, plus 200 to 300 millivolts. Below 40 to 50 millimeters in the sediments, the potentials were uniformly low, approximately negative 200 millivolts, indicative of extreme reducing conditions and total anoxia. The sediments remained oxidized to a depth of about 5 millimeters throughout the periods of summer stratification. Seasonal differences were observed in the sediment depth at which the transition from high to low potential occurred, but the region of low potential never extended into the water. After 5 months of thermal stratification, the point of 0 millivolts moved toward the surface of the sediments to negative to about 5 millimeters from approximately 12 millimeters at the time of spring turnover, and moved downward to minus 10 millimeters during fall circulation. The integrity of the oxidized macrozones was maintained in a thin but operationally very significant layer during stratification periods. The oxidized macrozone was further maintained by diffusion and by turbulent displacement of the uppermost sediments to the overlying water during turnover periods. The effectiveness of the oxidized macrozone in preventing a significant release of soluble components from the interstitial waters of the sediments to the overlying water was demonstrated in experimental chambers for over 5 months. Phosphorus in particular was prevented from migrating upward. So let's look at this figure before moving on here. Figure 15-4, diagrammatic profile of composite electrode potentials not corrected for pH variations across the sediment-water interface in undisturbed cores from the deepest portion of Windermere before, during, and after stratification. Okay. So let's see here. We have on the y-axis, we have the depth in millimeter. Then we have here the sediment-water interface, this horizontal line with these dashes. And then here we have on the x-axis, we have the voltage in millivolts, and where this is negative, and this is 0, and this is positive. So minus 200 millivolt to plus 200 millivolt. So, and we're therefore dealing with the deepest portion. This is Windermere, this is a lake in England, and so this is before the stratification. So there's also a time factor here that is not mapped. So this there's a before stratification, during the stratification, and after the stratification, probably. So, and then this is so therefore, like for example, at 40 millimeters, we have a potential of about it would be like about minus 210 millivolts. As we approach the surface of the water sediment surface, our potential is increasing, our voltage is increasing, so we have anoxic condition here. We're starting to get oxic conditions here, and so this is, there's like a temporal factor that is not mapped, and so then as you get really close to that interface between water and sediment, the potential reaches 200 and stabilizes at that value in the water. The ability of sediments to retain phosphorus beneath an oxidized microzone at the interface is related to several interacting factors. Much of the organic phosphorus reaching the sediments by sedimentation is decomposed and hydrolyzed. Most of the sediment phosphorus is inorganic, for example, apatite derived from the watershed, and phosphate adsorbed onto clays and aluminum and ferric hydroxides. Additionally, phosphate co-precipitates with iron, manganese, and carbonates, with proportions differing from watershed geology. Work on Wisconsin lake sediments and the Great Lakes indicated that phosphorus was present in the sediments predominantly as apatite, organic phosphorus, and orthophosphate ions covalently bonded to hydrated iron oxides. In calcareous sediments of hard water lakes containing 30 to 60% of calcium carbonate by weight, Calcium carbonate levels were not directly related to inorganic and total phosphorus. These sediments had a lower capacity to absorb inorganic phosphorus than non-calcareous sediments. The observation implied that calcium carbonate absorption is less important than iron phosphate complexes in controlling the concentrations of phosphorus in sediments. Major phosphorus bond fractions responsible for release can vary within a large lake. For example, in Lake Simcoe in central Ontario, phosphorus release from the sediments from deep glacially formed Kempenfeld Bay with a highly urbanized catchment is dominated by the redox-sensitive phosphorus fraction, whereas in shallow and agriculturally impacted Cooks Bay, the main phosphorus binding form that can be mobilized through diagenesis is carbonate bound phosphorus. Although phosphorus exchanged by adsorption and desorption within the sediments between sediment particles and interstitial water can be as rapid as a few minutes, the rate of transfer across the sediment-water interface depends on the state of the microzone. The oxidized layer forms an efficient trap for iron and manganese, as well as for phosphate, thereby greatly reducing the transport of materials into the water and scavenging materials such as phosphate from the water. As the oxygen content of water near the sediment interface declines, the oxidized microzone barrier weakens, as seen from Mortimer's experiments in Windermere. The release of phosphorus, iron, and manganese increased markedly as the redox potential decreased. With the reduction of ferric hydroxide and complexes, ferrous iron and adsorbed phosphates were mobilized and diffused into the water. The same general reactions were observed in the hypolimnetic water just overlying the sediments in eutrophic estuary water, England, a pattern that has been observed repeatedly in productive dimictic lakes since its initial detailed description by Ensley in 1936. A sudden release of ferrous iron and phosphate into the water occurs at the time when the plus 0.20 isovolts emerge from above the interface surface. This event is preceded by nitrate reduction and the slow release of bases, carbon dioxide and ammonia. As long as an abundance of nitrate remains and nitrate reduction continues in the overlying water, no release of iron-bound phosphate occurred from the sediment to the anoxic apolemnium. Manganese is reduced and mobilized at a higher redox potential than iron. So before we continue on, let's look at these figures here. Figure 15-5, variation in the chemical composition of water overlying deep water Windermere sediments over 152 days in experimental sediment water tanks. Left-hand series aerated chamber, right-hand series anoxic chamber. So aerated, oxic, anoxic on the right. A, distribution of redox potential. B, pH concentration of oxygen, pH concentration of oxygen and carbon dioxide in milligrams per liter. C, alkalinity expressed in milligrams of calcium carbonate per liter and specific conductance. D, iron, total and ferrous iron and sulfate in milligrams per liter. E, phosphate as P2O5 and silicon dioxide in milligrams per liter. And then F, nitrite multiplied by 100 and ammonia all as nitrogen in milligrams per liter. So that's a lot of graph here. So let's see. Here, the first one, we have oxic and anoxic on the right. We have the sediment water, the sediment surface, so the sediment water interface. So this would be the water. This is the sediment here. And so the A is the distribution of redox potential. So this is the redox potential in that chamber. So we have pretty linear here, where this is extremely variable on the right. This is the anoxic component, and then in voltage we have very negative as you increase with depth, and it gets positive as you get to the sediment water interface. Now we have The pH, so the pH decrease, so this is the x-axis on the number of days, by the way. So it decreases with the number of days. We have increases of oxygen, increases of carbon dioxide. This is in the anoxic chamber, and then this is the oxic chamber, sorry, on the left, and then this is the anoxic chamber here. pH is a little higher in the anoxic chamber, and then carbon dioxide also has a different behavior. We have very low oxygen, which makes sense in anoxic. So, going back here, what we wanted to point out is that we have stable voltages across time in the oxic chamber, where it's not stable in the anoxic chamber. And so here, for example, for whichever day that is, probably about 85 day, we have like this curve that shows I guess it would be the azo voltage line. So this line shows the voltage at that point here, for example. So the other voltage is minus 16 millivolts, I believe, at X day. And then that voltage becomes less and less negative as the experiment is ran. Alkalinity increases here in the anoxic chamber, and the conductivity increases, which is very different in the oxic chamber. Then we have sulfate concentration decreasing through time, total iron concentration increasing, as well as ferrous iron and manganese. Here we only have like the total iron increasing. All the other ones are not increasing whatsoever. Silicon dioxide, and then so we have different scales. This is the scale on the left here for silicon dioxide, and this is the scale for P2O3 here. And so silicates and phosphates, so pretty stable. A little increase at the end of the experiment here for silicate, definitely increase for silicate here, and increase for phosphate. And then nitrogen, pretty close to zero. All nitrogen species. Here ammonia increases significantly, while the other ones don't really change much, except for maybe a little bit of a nitrate peak here at the day between 76 and 89. All right, so then we have somewhat of a similar graph for 15-6, seasonal distribution and composition of milligrams per liter, and properties of water within 30 centimeters of the sediment at 14 meter in Islewaite water, England. Components as in figure 15-5, color in arbitrary units. So I'm not seeing any colors here, but I'll let you review this graph, which is kind of similar to what we just went over. Probably this is what they're referring to in color, an arbitrary unit, color being changed, being monitored and changing through time. Okay. I think that's it for that. So when we move on to this part of the section, the introduction of oxygen during, for example, optimal circulation to anaerobic waters causes ferrous iron to be oxidized and produces a simultaneous reduction of phosphates, part as ferric phosphate, which is less soluble than ferric hydroxide, and part by adsorption onto ferric hydroxide and calcium carbonate. Although manganese is oxidized more slowly than iron, it nonetheless is effectively precipitated at the time of overturn. Ferrous iron released from the sediment is often in excess of phosphate, and when oxidized, it precipitates much of the phosphate. Some of the ferric phosphate in particulate form may slowly hydrolyze and restore some phosphate to the upper waters and littoral areas. Although most phosphate is returned eventually to the sediment, much greater than 50% of the hypolimnetic phosphorus upwelled during autumnal circulation is available biologically. Often, however, other growth conditions are not optimal at that time of year. In very productive lakes, where hypolimnetic decomposition of sedimenting organic matter produces anoxic conditions and hydrogen sulfide, some ferrous sulfide is precipitated. Ferrous sulfide, like many other metal sulfides, is exceedingly insoluble and forms at a redox potential of about minus 100 millivolts. If large quantities of FeS, of iron sulfide, precipitate, sufficient iron can be removed to permit some of the phosphate accumulated in the hypolimnion to remain in solution during nocturnal circulation, although seasonal oxidation of iron sulfide precipitates can affect long-term accumulation rates. The addition of sulfate to a lake in order to increase the bacterial production of hydrogen sulfide and to accelerate the loss of iron has been suggested as a method of fertilizing lakes by regenerating phosphate from the sediment. Iron interacts with dissolved humic substances to bind phosphorus at acidic to near neutral pH values, irrespective of redox conditions in the superficial sediments of certain freshwater lakes. This process should enhance sediment retention of phosphorus in lakes with high loading of iron and humic substances. And that will be it for today, and tomorrow we'll pick it up with phosphorus release from the sediment. Thank you and have a good day. Bye.